Mutual independence of three events. Welcome, everyone. To begin our lesson today, let's take a look at our first slide, titled Mutual Independence of Three Events. Now, you'll remember from our previous lessons that we spent quite a bit of time discussing the independence of two events, specifically, how the occurrence of one event doesn't change the probability of another. However, as we move into more complex probability problems involving three or more events, the concept of independence becomes a bit more nuanced and requires a more careful approach. You might be tempted to think that if every pair of events is independent, then the whole group is independent, but that isn't quite enough. For a group of events to be truly independent, they must not only be independent when looking at them in pairs, but they must also be independent when considered all together as a single group. This higher level of independence, which covers both the pairs and the group as a whole, is what we formally call mutual independence. In the next few slides, we are going to break down exactly what these conditions look like and how you can mathematically verify them. Understanding the concept. When we talk about three events, A, B, and C, being mutually independent, we are looking for a very specific type of relationship. We need to ensure that there is no hidden connection between them. Specifically, we want to satisfy a set of conditions that guarantee that no single event, or even any combination of events, can give us any extra information about whether another event will occur. In other words, knowing the outcome of one doesn't change the probability of the others. To prove this mathematically, we can't just look at the group as a whole. We have to check two distinct levels of independence. First, we have to verify what we call pairwise independence, which we will break down in the next slide. Second, we must also satisfy joint independence, which we will discuss immediately after. We need both levels to hold true to claim that the events are truly mutually independent. Now that we've established that independence becomes more complex when we move beyond just two events, let's look closer at what this concept actually means. 1. Pairwise independence. Now that we understand that mutual independence requires two different levels of checking, let's dive into the first level, pairwise independence. Think of pairwise independence as looking at the events in small groups of two. It means that if you pick any two events from our set, they behave independently of each other, regardless of what the third event is doing. So, if we are working with three events, let's call them A, B, and C, we can't just look at them as one big group yet. We have to systematically check three separate pairs. First, let's look at pair 1, which is event A and event B. For this pair to be independent, the probability of both A and B occurring, which we write as the probability of intersection B, must be equal to the probability of A multiplied by the probability of B. Next, we move to pair 2, involving event A and event C. We apply the same logic here. The probability of intersection C must equal the probability of A multiplied by the probability of C. Finally, we check pair 3, which is event B and event C here. The probability of B intersection C must equal the probability of B multiplied by the probability of C. Now, a very important note. If even just one of these three conditions fails to hold, then we can immediately stop right there. The events cannot be considered mutually independent. However, keep in mind that even if all three of these pairs pass the test, we aren't finished yet. As we will see in the next slide, there is one more crucial condition we must verify to achieve true joint independence. 2. Joint independence. Now, this is a crucial point that many students overlook. Even if you have already checked all the pairs and found them to be independent, as we just discussed in the previous slide, it is still possible for the three events to be dependent when they occur all at the same time. In other words, the pairwise check isn't the complete story. Therefore, to truly claim mutual independence, we require one additional, fourth condition known as joint independence. This condition focuses on what we call the triple intersection. This means we must check the probability of all three events, A, B, and C, occurring simultaneously. For this to hold true, the probability of intersection B intersection C must be equal to the product of the individual probabilities. the probability of A times the probability of B times the probability of C. Once we verify this fourth condition alongside the three we just learned, we can move on to the formal definition and see how all these pieces fit together. Formal definition of mutual independence. Now that we have looked at pairwise independence and joint independence separately, let's bring everything together into one formal definition. On this slide, you can see the complete requirement for mutual independence. We say that three events, A, B, and C, are mutually independent if, and only if, the following four conditions are all satisfied simultaneously. First, we must satisfy the three conditions for pairwise independence that we just discussed. 1. The probability of intersection B equals the probability of A times the probability of B2. The probability of intersection C equals the probability of A times the probability of C and 3. The probability of B intersection C equals the probability of B times the probability of C. But as we will see in the next slide, pairwise independence alone isn't enough. We must also satisfy the fourth condition, which is joint independence. 4. The probability of intersection B intersection C equals the probability of A times the probability of B times the probability of C. It is crucial to remember this. If even a single one of these four equalities fails to hold, then you cannot claim the events are mutually independent. They are simply not independent as a group. Real-world example. Now that we have gone through the formal definitions and the four necessary conditions, let's put this theory into practice with a real-world example to see how it actually works. Imagine a scenario where we have three different people. Let's call them X, Y, and Z. They are all sitting for a mathematics exam, but here is the key. They are all in completely different cities. To turn this into a probability problem, let's define our three events. Event A is the event that person X passes the exam. Event B is the event that person Y passes, and event C is the event that person Z passes. Now, because these individuals are in different cities and have no way to communicate or collaborate on the exam, the outcome of one person's exam has no influence on the others. This suggests their results are independent. But, as we learned in the previous slides, to prove they are mutually independent, we can't just stop at pairs. We have to follow the two-step process we just discussed. First, let's perform step 1, checking for pairwise independence. We need to look at every possible pair. First, does person X passing affect person Y? No. So, the probability of both A and B occurring is equal to the probability of A times the probability of B next. We check person X and person Z, since X's result doesn't affect Z. The probability of intersection C equals the probability of A times the probability of C. Finally, we check the pair of Y and Z again. There is no influence, so the probability of B intersection C equals the probability of B times the probability of C. Now we move to step 2, checking for joint independence. This is that crucial fourth condition we talked about earlier. We need to see if all three events happening together follows the rule. Since no one's success influences anyone else, the probability of the intersection of A, B, and C, meaning all three people passing, is simply equal to the probability of A times the probability of B times the probability of C. Because we have successfully verified all four conditions, the three pairs and the triple intersection, we can confidently conclude that events A, B, and C are mutually independent. However, be careful. As we will see in the next slide, a common mistake is to assume that passing this step alone is enough. Let's look at what pitfalls you should avoid. Common mistakes. The most frequent mistake is assuming that pairwise independence automatically implies mutual independence. You might be tempted to look at a problem and think, well, I've already checked the three pairs, so I'm done. Specifically, you might see that the probability of intersection B equals the probability of A times the probability of B. And the same holds true for the pairs A and C, and B and C, and conclude that the events are automatically mutually independent. However, I must correct this misconception. This is not necessarily true. As we discussed in the previous slides regarding joint independence, it is mathematically possible for three events to be independent in pairs, meaning they pass all three pairwise tests, but still fail the joint independence test. This happens if the probability of intersection B intersection C does not equal the product of the individual probabilities of A, B, and C. So, the key takeaway here is that you cannot skip any steps. To claim that events are truly mutually independent, you must always verify that fourth condition. Never assume the group is independent just because the pairs are. Now, before we wrap up, I want to pause and highlight a very common pitfall that many students encounter when solving these types of problems. Key takeaways. First and foremost, remember that mutual independence is a much stronger condition than pairwise independence. As we discussed earlier when looking at the common mistakes, you cannot simply assume that because events are independent in pairs, they are independent as a whole. Specifically, for a set of three events, you must verify exactly four conditions to claim mutual independence. This includes 3 separate checks for the pairs and 1 final check for the entire group. To recap those formulas, for pairwise independence, you must ensure that the probability of intersection B equals the probability of A times the probability of B. The probability of intersection C equals the probability of A times the probability of C. And finally, the probability of B intersection C equals the probability of B times the probability of C. Then, you must satisfy the condition for joint independence, which is that the probability of an intersection B intersection C must equal the product of the individual probabilities of A, B, and C. Finally, keep this golden rule in mind. If even a single one of these 4 equalities fails to hold, you cannot call the events mutually independent. They are simply dependent. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's topic. I hope this clarification helps you approach these probability problems with more confidence. Great job today!